Hello and welcome to Say That Again Slowly, the Cambridge Festival podcast, where students interview the experts who have contributed to the festival. We try to pair up students and researchers from very different disciplines to bring things back to basics. There are no stupid questions here. This year's theme is power in all its forms, from nuclear energy to medieval saints, from the history of money to the biology of extraordinary animals. I'm Beth King and I'm studying for an MPhil in Classics. And today I'm interviewing Susannah, Michael, and Hugh about nuclear energy. So to get things started, would you like to just introduce yourselves and how you got into nuclear energy?
Hi, I'm Susannah, and I'm currently studying for a PhD in nuclear materials. So I particularly got interested in nuclear during my undergraduate and have since just become quite interested in the industry through work in our Centre for Doctoral Training, our CDT, which is based in nuclear.
Hi, my name is Michael Salvini. I'm a second year PhD student at the University of Bristol in mechanical engineering. My research is mostly surrounding sort of computational modeling of nuclear materials. So that's like structural components in reactors. Yeah.
Hi, I'm Hugh Dorward. I'm also at the University of Bristol with Michael in the same research group, looking at, again, nuclear materials. Particularly my project is looking at applications for machine learning within nuclear materials. And I'm also part of the nuclear CDT, which I kind of just got into by learning a bit more about nuclear over lockdown and decided to apply for a PhD.
Great. I know very little about nuclear energy. Most of the stuff I do is 2,000 years ago, if not more. So your science fair section is about the future of nuclear energies, right? First, though, I thought it might be interesting to talk about the past of nuclear energy, and how nuclear science has developed in the last few years.
Yeah, I guess I can start. A lot of the focus of our Centre for Doctoral Training is in what's known as Generation 4 reactor technologies. And this came out of a forum, I think sometime in the 2000s, to identify what were going to be the kind of future reactor types to tackle things seen as issues within nuclear energy production. What's quite interesting about those reactor technologies is a lot of them aren't actually particularly new. A lot of them based off experiments in the early days of nuclear power in the 50s and the 60s and things. And it's just that with things such as advanced materials, scaling those up has seemed to be more attractive or more feasible now. Don't know if Michael or Susannah have anything to add to that?
Yeah, I was going to say, just to add to that, that sort of nuclear power, particularly in countries like the UK, has been around for many, many years. So even at this point, we're trying to extend the life of reactors beyond their sort of 60-year limit that was initially given. But we've got new technologies, new materials. That means we can extend those lives even further. So nuclear power isn't necessarily a new thing. For example, even there's nuclear fission happening on the sun and has been for billions and billions of years. The interesting thing about moving forward in the future is that we can make it even more efficient. We can make it even more of a viable energy source for more and more people.
Yeah, I think it's kind of just worth outlining that ultimately nuclear power and nuclear energy is all about coming up with at the end of the day a more advanced kettle. Ultimately, we're just looking to heat water, to create steam, to turn a turbine and generate electricity, much in the same way that we have been for 100 years now. And like you said, it's quite often we end up using and recycling these same ideas and these same principles that come through. And actually, especially now with the kind of future technologies that are coming around, it's all about refinement and there are issues that we want to solve, relating to how long we can run them for, and so we develop newer materials and newer techniques in order to try and go about improving that. And that kind of covers every aspect of a nuclear power station's life cycle. So that's from the very early design to the initial operations, to the issue of waste, the issue of decommissioning, and so it kind of encompasses all of those things, which is, I guess, as well as so much exciting research going on these days.
Yeah, I think that issue of waste is obviously a really important one. So can you explain for a complete novice how nuclear waste is produced and why it's so tricky to deal with?
So we kind of have a few different types of nuclear waste. So that might include, for example, things like structural components in your reactor, the thing that's actually holding all of your fuel and the reaction itself. And then you might have a different type of waste, like the kind of containment equipment, and that might be the day-to-day equipment used by staff in operations and things like that. And then I guess you've got the one that everyone's up in arms about or thinking about all the time is the fuel itself. And so typically what will happen is your fuel at the end of your life cycle might be removed from your reactor, and stored or vitrified in glass and ceramics, and then those might be set for deep geological disposal potentially. But I think it's always worth mentioning that actually, although the waste itself can be very, very harmful, that the actual quantity of waste that we're producing in these operations kind of really very much scales with the sort of how serious it is. So your low level waste, you might have a decent amount of it, but actually it's pretty very low levels of radiation be given off that. Whereas the real sort of high level stuff that people are really concerned about, actually, if you took the amount of high level waste that is produced by a reactor, and if we use that to power the entirety of the UK for an entire person's lifespan, the amount of high level waste that each of us would be kind of responsible for, as it were, is about the size of your fist. So it's a very interesting problem in that it's serious stuff that has to be handled with care, but actually, the entire power need of the UK could kind of fit inside of a room, and quite a large room. But it's an interesting prospect when we especially compare that to kind of how much attention these sorts of issues get when we kind of discuss them in public.
Yeah, it's definitely one of the main issues I've heard about, and that's from a very fringe perspective. But it is an issue but it seems at least quite scary. So that's in some ways reassuring to know that it's not as much waste as people make it seem. But it does still seem like an issue that is only going to get bigger if we do turn to nuclear energy more, as maybe we should. Then surely the waste is just going to keep growing, and that's going to be a growing problem rather than a problem that plateaus.
Yeah, I think if I can jump in, I think one important thing to note is we hear a lot about the UK's waste at Sellafield. The vast majority of that is legacy wastes, a lot of it not even related to civil nuclear energy generation. It's from the UK's nuclear weapons programme in the 40s and 50s. The way that reactors run now in the UK, we've moved to what's known as a closed fuel cycle. So the fuel that comes out of the reactor at the end of its life is put straight into containment and is sent straight to storage, and then in the future the plan is for that to go into deep geological disposal. And Michael mentioned the kind of scale of that. I've heard it as one person's waste for their lifetime of it in a Coke can. I think the other thing, one of the reasons that we talk about waste in the nuclear industry a lot is because the nuclear energy industry is actually one of the few industries to actually consider its waste through its whole life, because it has to. Oil and gas industry, for example, doesn't, because if you think of a Coke can full of high level spent fuel compared to all the tons of CO2 that would be equivalent from oil or gas, that's not considered by oil and gas, for example.
Yeah, I hadn't thought of it like that, about other industries not thinking about waste and just pumping it out into the air and it doing even more damage. Um, so what was the something ecological? Is that putting the waste underground?
Sorry. Yes. So it's the plan is the idea is that it's known as deep geological disposal, and unfortunately none of us are working on a kind of waste end of the nuclear cycle in our projects. There are people in the group who do, but this is to do with burying the stuff deep underground where there's lots of barriers to prevent there being any radiological contamination. And this is through lots of different materials, lots of different layers of protection, concrete, clays, and then it's buried very deep underground. There's been plans in the UK for developing it. I think it's either Sweden or Finland. I think it's Finland, has quite advanced concepts and development going on into storing it. And I'm not sure on the actual depths that people look to bury it. I'm not sure if Susannah or Michael know.
No, I was going to say I'm not exactly sure about the depth, but someone in our CDT, I know, Tom, who's working on this, will be at the Cambridge Festival and is willing to talk about it. But I know he's particularly looking at sort of vitrifying the waste, so that means sort of encasing it in glass, as mentioned before. And the thing is, what he has to do is prove that during the time that it takes that waste to get down to sort of background levels of radiation, so sort of the radiation levels that we experience every day from natural sources like granite or just naturally occurring minerals and rocks in the environment, he has to make sure that the vitrified waste can basically be contained for that length of time. So there's a lot of development into how we can encase the waste until it gets down to sort of safe levels or everyday levels that we're used to.
Yeah, that's very interesting, especially as a classicist. I spend a lot of time thinking of or digging up things buried thousands of years ago. So that's an interesting area of it for me. But maybe now it might be good to look more at the future of nuclear energy. You talked about how a lot of the technology is from the 50s and 60s. How is it changing now for the future? What are the main aims going forward?
I think one of the big things people are looking at is alternative uses of nuclear beyond just producing heat for electricity production. And if you can, one big advantage of nuclear power is if you can get higher efficiencies, higher output temperatures, you can get temperatures which mean harder to decarbonize areas in industry, such as things like steel production, producing hydrogen. That becomes feasible from one of these kind of very high temperature nuclear reactor options. These are obviously currently very high carbon intensive things. This is what requires the coking coal, which this new proposed coal mine in Cumbria, I think, was to provide coking coal for the steel industry. So that's one big advantage if these technologies can get to these high temperatures. Another is potentially using fuel more efficiently. So being able to either look at different fuel cycles, because traditionally it's the uranium fuel cycle, which requires uranium 238 and 235. But potentially some of these reactors could look at thorium fuel cycle. And thorium is extremely abundant. So there's lots of years of fuel potentially available if reactors can work using a thorium cycle.
Would thorium be safer than uranium? Is that a consideration there?
Well, you're sort of the way that your thorium fuel cycle works is that you are essentially loading thorium into your reactor, and it'll from that you then produce other fissile isotopes. So your thorium can then be converted to uranium within your reactor. So the idea is that uranium, I think if we stepped up our supply and production of uranium, we'd have about enough uranium to kind of power and to meet global demand for, I think it's the next sort of 100 years or so. Whereas, in theory, if you're able to switch to a thorium fuel cycle, you'd be looking at, potentially 1,000 years or several hundred years of enough fuel to meet global energy demand. So that's the kind of real big advantage of that. And of course, with a large supply of these types of fuels out there, that can then also, potentially bring down cost later on down the line. So I think that's a big appeal for why certain countries are certainly looking into that. I know I think India are very interested in thorium fuel cycles, mainly because they have some of the largest thorium reserves in the world. But it's certainly an interesting way of doing things a little bit differently.
And on a maybe more basic level, where does the thorium come from? How is that obtained? Why do some countries have more and some countries have less?
Yeah, I think we could really do with one of the geologists on here now. But like uranium, it's mined from ores in the ground. And yeah, unfortunately, my geology has never been particularly good. But for the same reasons that there's distributions in uranium and all sorts of elements in the Earth's crust, that leads to this kind of heterogeneity and where they can be found on Earth.
Yeah, I think the one of the sort of advantages that you sometimes see with nuclear fuels, at least compared to sort of oil and gas and fossil fuels, is that the way that these kind of things are distributed across the Earth very differently to how fossil fuel reserves are. Fossil fuels form, places that used to be seabeds or lake beds, and that's where you can kind of get these deposits of oil and gas and things like that. Whereas the way that nuclear fuels and elements like uranium and thorium are distributed, they kind of form from when our planet first formed, 4.5 billion years ago. Those kind of clouds of rock and gas and dust that have kind of coalesced into a planet. And what it means is that actually, you get this very homogeneous distribution of these elements around the world. So, for example, if you look at uranium distribution, you find that there's no single country that has 50-60% of uranium supply, and you certainly don't see it concentrated in 10 or 12 countries around the world like you might do with oil and gas. So it's even just from that sort of perspective, it's kind of seen as maybe slightly more stable, because you're not relying on currently politically unstable regions in the world to supply your fuel. For example, Australia and Canada have very large supplies of uranium. Even the UK as well. I think there were quite large uranium mines down in Cornwall.
Yeah, and just even building off that, something quite interesting that I heard was that because there are these large stores, sometimes we get basically what we call natural fission reactors going on. So if there's sort of some uranium compressed underground, I think they've seen it in America a few times, where basically what we're doing artificially in reactors occurs naturally as well. They see the production of the similar isotopes that we see in reactors. So all based on quite a natural process.
So then the idea of the reactor is to, or the research unit is to recreate that natural reaction. That makes it sound very, yeah, very sustainable and stable, and nothing at all like the kind of disaster-prone outlook on nuclear energy that I think you see quite a lot in the media and kind of popular imagination. For the festival on Saturday, what can people expect to find and to learn from you guys?
Well, I think it's a chance to kind of meet some of the young researchers who are kind of stepping up into this field. So you can feel free to come and talk to us. We've all got areas of what some of us might call expertise. I'm not sure whether you'll have to come and decide that for yourself. But we've got research interests in a whole wide range. So that's from designs to modeling to waste and decommissioning. And that's whether you want to talk to us about our research or, talk to us about nuclear energy as a whole. If you disagree with the idea of it, if you think it's, the best thing since sliced bread, come and kind of engage with it and learn a little bit more. And then outside of that, we've kind of got some little activities and demonstrations to try and maybe teach people a few things that they might not have known about how a nuclear reactor works. And there's always a lot of talk about reactors being critical and subcritical and supercritical, but actually criticality is not such a terrifying term as hopefully people will find out if they come along.
I've got to admit, I've never heard criticality used in a context like that. What does that mean?
Well, I think critical, most people's daily lives is quite a terrifying term if something's critical. But it basically just means that the reactor is operating normally, essentially. So if the keeping criticality is just making sure that the reactor is functioning, the same amount of power is coming out consistently over time, and that actually it's stable and easy to control in kind of lay terms, I think.
Yeah, and just to add to what you can sort of expect at the festival, we've kind of put it in the terms of a sort of fun fair theme. So to try and present nuclear maybe from a different side, sort of in a way you maybe haven't seen before. So there's traditional things like hooker duck, coconut shy style thing, but all with a nuclear take on it. So you can learn a bit more about shielding used in reactors through a coconut shy and activities like that. So hopefully to dispel some myths and also give a bit of an insight into the nuclear industry, but in a way that's hopefully accessible to most people and families as well.
That sounds great. How does a coconut shy replicate a nuclear reactor?
So sort of with a nuclear reactor, something you want to do as a similar way to the waste is contain any radiation that's produced during the reaction that's taking place. So we use special materials surrounding these reactors, and the people who've set up this coconut shy, they do their research into these materials and can tell you more about them as well. But basically what we're trying to show is that some materials are more effective than others. So you can give it a try, see if you can knock the coconuts off, depending on what sort of shielding's in place, and also understand a bit more about how we engineer materials to make sure any radiation that's produced can be contained inside.
That sounds like a lot of fun. Which are the things at the festival that relate to your areas of research? Which are your favourite bits of it?
I mean, I can so a lot of my work is kind of in material properties and things like that. And one of the things that I've been putting together recently is a demonstration of, it's something called a Prince Rupert drop. But it's basically a kind of droplet of glass that you solidify in cold water, and it forms this kind of sort of tadpole shape object with a really kind of long spindly tail, with some really, really unusual properties. So this is a kind of tadpole shaped piece of glass that you can hit with a hammer, and will just be absolutely fine. And you can, I've seen people shoot them with bullets. You can drive over them, do all sorts of things, but it has this tiny long spindly tail, whereas if you kind of clip the tail even slightly, it just immediately explodes into kind of dust. And it's just the coolest demonstration I've ever seen live. So as soon as I had the opportunity to kind of do it myself, I was definitely going to jump on that. And it's a really interesting demonstration of something called residual stresses, which is something that forms in these glass when they just kind of cool really, really quickly. That basically just means that the kind of bulb of this tadpole is just really, really strongly held together, but only on the outside, and on the inside is incredibly fragile. And so that kind of fragileness kind of extends into the tail. So you get this really hard outside on this tadpole thing, and then this really, really fragile tail. But it's a really cool thing to see in person.
Yeah, that's amazing. That sounds like magic.
It kind of feels like that a little bit, yeah.
Where's the bit of the nuclear reactor or energy chain that is like that?
Sorry, yeah. Well, I was going to say, luckily, the nuclear aspect is not relating to the exploding. But no, so a lot of what goes into kind of material design in these reactors is all about kind of taking advantage of all these material properties and ways of producing materials. And so the use of residual stresses, and kind of learning how we can produce materials that have these kind of very hard and are very strong materials that we can build our reactors with, and knowing then that those can withstand all of the kind of conditions that are within a reactor, is super important. So it's a very cool demonstration of a property that is kind of being used right across kind of materials engineering, but in particular in nuclear energy.
Yeah, I would just add to that and say that all three of us, I think, are involved in particularly looking at stresses within materials and understanding the stress states within something. So sort of where those high stresses are, where those low stresses are in a piece of material is really, really important to understand how it will behave. And we can use sort of computational modeling, so using computer programs to simulate that, as well as experiments in real life. And so there's a lot of research into that, looking at things right down to sort of micro scales or even nanoscales. That's sort of times 10 to the -9 of the meter, right up to the macro scale, so what you can see with your eye as well. So understanding how materials behave can be done on all length scales.
And I think there's touching on that kind of computational and the experimental side of material science that we look at. I think there might be an example of that on Saturday, based around the kind of thermal hydraulic side, which is the flow of the coolant water in a nuclear reactor. There's a demonstration which has essentially an experimental rig with some bubbles forming, and I think some cool lights to light up and demonstrate how the temperature changes. And then alongside that, there's there'll be a laptop showing a simulation of the same thing to demonstrate how we can use these kind of computer experiments to predict and demonstrate what's going on inside reactor systems or materials or whatever.
I don't know if it's possible to explain in simple terms, but how does the computer know what's going on inside the material?
So computer modeling, the key thing about it is sort of any model that's produced needs to be what we call validated. It needs to be checked against some sort of experimental result, and then after that you can build up your confidence in it, and then it can predict something that maybe you couldn't predict so easily through a physical experiment, because you validated it with experiments that are available. So basically, sort of this computational modeling works in parallel with experiments. So for example, if you did a test on a piece of material and you found out how hard you need to sort of stress it or bend it in order for it to break, you can then feed that information into a computational model. And then that could potentially tell you how that crack started in that material. So you can sort of use both experiment and computational modeling in tandem to understand the full picture of what's going on in a piece of material.
Okay, so we've talked quite a lot now about the power of nuclear energy, but the Cambridge Festival theme of power is more about, or is also about power more broadly. And I'm guessing quite a lot of the power behind nuclear energy comes from the power of investment and the power of governments to do different things with it. How does that power balance affect your research? What do you think about it?
So probably something to always bear in mind is that nuclear reactors can be quite expensive. That's sort of a fact surrounding them. And often they take either government investment or some sort of hybrid investment between governments and a private investor. And historically, that has been a bit of a problem for nuclear power. For example, because reactors can sometimes have fairly long lead times to be built, or initially it looks like quite a large investment that will ultimately pay off, but you always have to explain to an investor that they will get their money back, but it might be in several, potentially 10 years' time. And historically, that has been a problem with nuclear power, which is actually why, so at the moment, there's a lot of research into what we're calling SMRs, which are small modular reactors. And the idea of these reactors is they're much smaller. So you don't need such a large land area. They're much quicker to build because that's the modular idea, the idea that we can build lots of the same thing in specially designed factories. So it makes it much easier. You can get sort of economies of scale through that sort of route. And it's quite a new technology, but the sort of the fundamental processes that take place are things that we understand really well already. So this idea of scaling reactors down, so they're sort of cheaper, easier to build, there's a lot of research going into that at the moment. And sort of as Hugh indicated before, the idea of these small modular reactors are that they could both provide power for electricity purposes, but also potentially for industrial purposes like steel making as well. So that's quite an interesting area going on at the moment.
So where does most of the nuclear energy and power go to at the moment? Who's buying it?
Currently, we're buying an awful lot of it. So I think, we produce about sort of 15% of our kind of total energy demand of our own. France, I believe, they're about 70%. And so, in this kind of age of globalized energy markets, we're buying an awful lot of nuclear energy, nuclear electricity from France as it is. The same kind of applies, across Europe. I know Germany, very, very hesitant towards building nuclear power stations, but they're more than happy to buy an awful lot of their power from France. So, at the moment, it's being primarily used for electricity production here in the UK. But as kind of Hugh touched on earlier, it's the big advantage being that we can use the same technology but kind of aim it in different directions. So one idea with the small modular reactors is that a large steelworks might not have the need for a Hinkley Point C sized reactor producing high temperature gases for steel making. But if they can have a kind of small modular reactor on site shared between them and potentially a couple of other factories nearby, you can massively kind of decarbonize those industries and at a much lower expense. I think that the cost of Hinkley Point C is looking to be about 30 billion pounds. The cost of one of these small modular reactors would be closer to 2. And so all of a sudden you're taking out this big kind of roadblock in the way of that kind of high upfront cost. That means that not only can you build far more of them far quicker, but actually the kind of industry and the kind of company and the size of investment means that far more people can kind of benefit from being able to build a small modular reactor, and that's both in the UK and abroad. I know there are kind of deals and memorandums of understanding and things like that are being written between various countries in Europe. I think Poland and the Czech Republic have recently cottoned onto the idea that small modular reactors might be a viable option for them.
So that sounds like it's a very global project. How global is the research? How much does research from other countries come into your research? And what's the communication like between the scientists? Physicists are terrible at talking across country borders, so it'd be interesting to see if it's different.
Well, sorry, Hugh, do you want to take that on?
No, you crack on. That's fine.
I was going to say, scientists love nothing more than communicating across borders, especially if it means there's trips and conferences involved. Nothing we love more than that. But traditionally, especially in kind of nuclear science, communication has been on a far more limited scale. We've always had companies and governments trying to protect information and research that's being done in the field of nuclear energy and nuclear engineering. And you're seeing a little bit more, especially now that we're starting to move to more private companies being involved in nuclear power, that there's a little bit more communication, and there's a little bit more cross-border control. So for example, in my research group, we've got researchers who are being funded by French engineering authorities and nuclear authorities. I do a little bit of my work with EDF Energy, and I know that lots of large French engineering firms, because typically, as a result of so much of their energy supply coming from nuclear energy, France is really one of the leaders in nuclear research. So as a result, there's always going to be a lot more cross-border communication between scientists.
Yeah, I think it's interesting going back. Obviously, we're all in this kind of materials research field, and sometimes the actual the funding and the CDTs through nuclear, but a lot of the work we do is applicable beyond the nuclear industry. So in that regard, it's more sharing information and research about our specific field. But touching back on the small modular reactors, there is, I think, a fair bit of sharing, but a lot of these are done by private companies, and I think it's seen as a bit of it will be quite a good prize for the country who has the company that develops an SMR that's going to be sold around the globe. And I think there's almost a bit of a race which is driving innovation in the area to be the first, because of these potentials of selling reactors to other countries across the globe.
Right, so the competition sort of helps and hinders the different countries. Do you think the close connection to nuclear warfare with nuclear energy is also a contributing factor there?
It's certainly a sticky point when it comes to nuclear energy, not least in terms of the public perception. So the technologies themselves are very, very different, but the use, there's a lot of similar terminology that means you kind of can't help but it's escape that comparison, whether that's in the media or in just sort of public opinion, or in sometimes in policy making as well. A lot of reactors nowadays are, and especially a lot of the kind of newer designs that people are researching today, one of the big focuses is non-proliferation, ensuring that waste and fuel for these reactors can't be used in any way for nuclear weapons. And that's one of the things that the UK has been going for of a closed fuel cycle, and looking at those kind of different things is ensuring that fuel then can't be turned into nuclear weapons. But it's certainly something that the sort of the energy industry has really tried to distance itself from. But how successful that is kind of depends on I guess the person who's looking, really.
Yeah, I'd probably just add to that and say, so with nuclear power, there's sort of two types of power. There's fusion, which is splitting stuff apart. Fusion, which is pushing stuff together, sorry. And there's fission, which is splitting stuff apart. And particularly the fusion side, this is exactly what goes on in the sun. That side of the industry has managed to distance itself quite far from the concept of weapons, which traditionally fission based. And because of that, in terms of international cooperation, it's made great leaps. So there are sort of joint research ventures such as ITER, which is a research reactor currently being built in France. It's a collaboration between multiple different countries. And so from that side of the nuclear industry, there's a lot of cooperation, and it's very much seen as a viable energy source for the future. But yeah, as Michael said, it's very different sort of using nuclear power for energy purposes to the weapons purposes. And the industry's made a lot of progression moving forward in terms of security and non-proliferation.
That's very good to hear. I think I had probably assumed that nuclear energy research and the technology behind nuclear atomic bombs and things went hand in hand. But that's a good myth buster.
I guess very briefly, if we're talking a bit about the politics around nuclear, I just add, I guess, that it's quite an exciting time in nuclear research for nuclear power generation at the moment. It seems, in this country at least, both main political parties are quite committed and see it as part of the future energy mix. And at least for the moment, it looks like there's a lot of drive for development in it. So it's a very exciting field. So if you want to come along and learn more about it and potential avenues to get into it, come along on Saturday to the Cambridge Science Festival and see us there.
Yeah, I think the last thing I would just add is that we can try and address myths here, but actually, yeah, if anyone listening has a kind of burning question or something that they want dispelled or anything like that, then yeah, best come along and just have a chat with us. There's so many of us there with lots of diverse backgrounds who can, as a result, can kind of cover a lot of different issues. Yeah, come along on Saturday the 23rd, 25th.
Yeah.
And you get to try coconut shy and see an exploding tadpole. So I'm sold. I want to say thank you so much to all three of you, Susannah, Michael, and Hugh. I've learned masses in the last hour or so about nuclear energy. And I would absolutely encourage anyone who's around this Saturday, the 25th, to head over to the Cambridge Festival and see you in person. Also, make sure to follow the Cambridge Festival on Facebook, Twitter and Instagram and YouTube for more fascinating events, and follow the Say That Again Slowly podcast for more conversations with this year's experts on the theme of power in all its forms. Thanks everyone for listening.